Hello, everyone. Thank you very much for joining us today for the webinar called The Cold Economy, A New Approach to Cooling. I hope you're all doing well during this latest lockdown. My name is Jack Tretui. I am the Outreach Officer for the IMechE Yorkshire Humber Processes Division and today's host. And it's my pleasure today to introduce today's guest speaker, Dr. Tim Fox. Tim is an internationally recognized expert on clean energy, sustainable food systems and climate change adaptation, with a particular focus on rural communities, cooling, and developing economies. He has been lead author of numerous peer-reviewed papers, research reports, thought leadership reports, and policy papers, and he has been featured in hundreds of press articles, op-ed pieces, and broadcast media appearances. So we really are in good company today. This introduction is going to be followed by a 40 to 45 minute talk given by Dr. Tim Fox, and then there'll be about 10 or 15 minutes at the end where you can ask any questions that you have to Tim. And with that, I'll pass you over to Tim and let's get started.
Thank you very much, Jack. Many thanks to all of you that have given up your time this morning to join today's webinar. I hope you're going to find it fascinating and that it provides some insights into what's probably an area that many of you haven't really given much consideration to from an energy sustainability and engineering perspective. So, as Jack said, my name is Dr. Tim Fox, and I'm the chair of the Institution of Mechanical Engineers Process Industries Division Board. I'm also an independent consultant, and my area of subject matter expertise, as Jack highlighted, covers both mitigation of climate change, so reducing emissions to reduce future climate change, but also I do a lot of work on adapting to climate change. That is ensuring that our systems are resilient in the face of the climate change that we will experience as a result of past emissions, and indeed emissions to come as a result of the emissions trajectories that we're currently on. And this whole area of work around the cold economy and a new approach to cooling is really a synergistic combination of those two areas of my particular professional interest. It's all about adapting to future heat, but it's also all about mitigating the emissions from cooling systems to ensure that that future heat doesn't go much higher than we're currently projecting at the low emission scenarios. So, in terms of the talk today, it's based on work that I've done both as chair of Process Industries Division Board, but also as an independent consultant, and it features a lot of work from expertise in the area. Most specifically, Professor Toby Peters from the University of Birmingham, who is one of the world's leaders in thinking about cooling, and indeed the world's only professor of cold economy. So let's ask ourselves the first most sort of fundamental question: why does cold matter? Why do we need to think about cooling? And many of you probably don't appreciate the scale of the cooling, and it's the way in which it underpins modern society. Cooling is so ubiquitous around us that we take it for granted, and we don't really realize how much of a contribution it makes to enabling us to function in our current socio-economic mode. So let me just give you a couple of examples to get the thought processes going. So around 70% of the food that we produce here in the UK and indeed across Europe is chilled or frozen. And in fact, if you just take a walk into your local supermarket and look at the amount of chilled and frozen produce that is within the supermarket, you'll quickly realize that a large portion of the supermarket's energy demand will be coming from the provision of electricity to drive that cooling. And in fact, if you ask a supermarket manager, they'll tell you that around 55% of their energy bill is allocated to that refrigeration technology that provides all that cooling. And that's only really the tip of the iceberg, if you'll forgive the pun, because the cooling system that has to support that that produce that arrives in the supermarket in that condition, it's a system that is called the cold chain, which is a seamless end-to-end system of temperature-controlled environment from the farm or the fishery through to the consumer. Consumes enormous amounts of energy. And indeed, if you just consider the refrigeration component alone, it accounts for around 70% of global electricity supply. Indeed, here in the United Kingdom, around 16% of our electricity supply is used in refrigeration. So moving on from the food system, if you start to think about what we're using today, the IT system. So here we are doing a webinar. Many of you are probably checking emails on your phone and things at the same time. And you'll be plugging into and interacting with data centers. And data centers are enormous consumers of energy. And a lot of that energy is involved in the cooling of the servers. So around 50% of a data center's energy bill is associated with cooling of the servers. And only around 50% of the electricity consumed by the data center is actually used for the processing. So, there's another good example of how cooling is a ubiquitous part of modern life. And indeed, if you start thinking about comfort, and you think about hot, warm days and the impact of heat on workplace productivity and educational productivity, then it doesn't take long to realize that there's a significant economic cost to that, as well as a social cost to that, for a country like the UK. And indeed, it's estimated that around 15.7 billion euros of lost productivity occurs per year as a result of a lack of cooling. And of course, very, very poignant for today's pandemic situation is the fact that we rely, and many of you will have become significantly aware of this in the period just before Christmas, with the release of the various vaccines being approved and put into the supply chain, that we rely on a robust cold chain for the delivery of vaccine. And indeed, many of us have known for some time that the world's vaccine distribution system is not completely adequate and fit for purpose. Indeed, around 25% of liquid vaccines are wasted every year because of the lack of cold chain facility to get them, capability to get those vaccines to the point of administration in developing and least developed economies. So you're getting the picture that cooling is a significant part of modern life. And in fact, I've listed here a range of areas that cooling is absolutely fundamental to. We've talked about the food system. You can see the range of steps within the food distribution system and processing system, and hospitality and retail elements, and indeed right the way through to the refrigerator in your home, in which cooling is important. It underpins many aspects of the energy system, not only in cooling of energy plant, but also obviously it's becoming increasingly used in thermal energy storage, and we're looking a lot more now at waste heat and cold recovery systems and district cooling systems. We've already mentioned healthcare with vaccine and medicine production, transport, and storage. The built environment, looking at personal comfort, domestic, commercial, and public space cooling, both in terms of making sure that we're personally comfortable with it in our homes, but also, of course, in our workplace and educational settings. Digital technology, not just data centers, but many different devices and elements in the IT infrastructure require cooling. In transport, obviously, a key point in that distribution chain or that supply chain is the transportation of vaccines or food, and the provision of vehicle payload bays with cooling is absolutely fundamental to that. You cannot have a seamless temperature-controlled cold chain from point of production to point of use without having a mobility or vehicle-based system within there. In terms of our area of interest at the Process Industries Division Board, industrial gases, liquid natural gas, liquefied hydrogen, all of these are processes that require very low temperature, and use enormous amounts of cooling, which is generally produced through electricity use. And of course, there's industrial scale chilling and freezing processes. And increasingly so, as mines get deeper, cooling is becoming ever more important in mining activities, both in terms of the vehicles and tools that are used in the mine, but also personal cooling and ventilation. So how do we actually deliver this cooling? Well, there are three core areas that we think about when we're working in cooling. There's the space, what we call space cooling, which is basically the cooling that we provide for human comfort in buildings, whether they be domestic or commercial settings. And this typically uses air conditioning units. You see here in the picture, individual air conditioning units strapped to the outside of flats in Mumbai, and this is a typical solution using individual air conditioning units to deliver cooling to internal space. Stationary refrigeration, so that's equipment that's used in buildings, either residential, commercial, or industrial. Right from the domestic refrigerator most of you will have in your home or your flat or wherever, right the way through to the very large-scale cold stores used in food and vaccine distribution centers. And then, as I've mentioned, there's mobile cooling, but of course not only associated with the movement of freight in terms of food and vaccines, but also increasingly so in public transport, buses and coaches and trains, and indeed in your own personal transportation vehicle, your car. And of course, this demand for air conditioning is set to increase as we move into a hotter, warmer world as a result of climate change, which of course is partly where the adaptation interest comes in. So all of this cooling, of course, is absolutely fundamental to the developing economies of the world. And I've just got a couple of slides here that give you an indication of how important cooling is and is going to be for us to achieve the Sustainable Development Goals set by the United Nations. And I'm not going to work through these, but when you have an opportunity to look through these in the recording of the webinar, you'll quickly get a sense of how it's fundamental just in these two cases of the provision of cold chains and provision of space cooling, both today and indeed in 2050. Of course, for those of us that work in the energy system and are interested in mitigating climate change emissions, we need to understand what the energy consumption is of the cooling system, and we also need to understand what the emissions, associated emissions are. So I've just provided a couple of charts here from some work done by Toby Peters at the University of Birmingham and his team there, looking at what the current energy consumption is. It's slightly outdated data now, but it's from 2018, only a couple of years ago, and it gives an indication by sector and by region of the sort of percentages involved in each of those application areas that I spoke about: space cooling, stationary refrigeration, and mobile cooling. And indeed, these pie charts represent a total cooling consumption currently of around 3,900 terawatt hours a year. And if we look at how that distributes around the world, you can see that a significant amount of cooling energy use is now based in China, which may be surprising to some of you. You might expect that the number would have been associated with the USA and other advanced economies and advanced economic blocs like the EU. But indeed, the uptake of cooling, both in terms of refrigeration, cold chains, and building space cooling in China has been phenomenal in recent times. So, for example, China has gone from a point back in 1995 when it only had 7% of urban domestic fridge use, whereas now in the urban domestic setting, about 95% or in fact, by 2007, 95% of the urban households had a domestic refrigerator. So turning to emissions, total emissions from in terms of greenhouse gas CO2 equivalent emissions in 2018 were around 4 gigatons, which is a substantial component of the global emissions. And in fact, again, you will see that how this divides between the space cooling, mobile cooling, and stationary refrigeration, and indeed regionally around the world. One of the key things I need to stress here is that emissions from cooling systems come primarily from two sources. There is the direct emissions associated with leakage of refrigerants themselves, either in air conditioning units or refrigeration systems, and this is the leakage of in many cases high global warming potential refrigerants, which are particularly destructive. And of course, these can be several thousand times more impactful per gram than CO2. In fact, 2,000 to 4,000 times more. So any leakage of refrigerants is a significant emission. And then, of course, there is the emissions associated with the electricity use, which in many parts of the world is still heavily fossil fuel based. And in fact, if you think about China and India, heavily based on the burning of coal. So in terms of the scale, around 30% of the emissions come from those leakages or incorrect disposal of refrigerants, and around 70% actually comes from the power generation system. So that's where we are sort of roughly today. Let's have a think about where we're going to be going in the future. So I just want to spend a couple of moments looking at the cooling demand drivers. So of course, superimposed on all of this is the fact that we're living in a world that is getting warmer, and that the future holds hotter, drier conditions in summer in many places of the world, particularly here in the UK, and indeed in many cases warmer winters. And this is going to potentially lead to a reduction in heat demand and an increase in cooling demand. And if we then have a look at the sort of the socio-economic aspects of that climate change impacts is integrated with, there is sort of a headline figure, as many of you will know, that about 75% of people on the planet will be urbanized by 2050, and the majority of these, of course, are in areas of the world that are developing economies. And alongside this urbanization, typically in social terms, comes some growing affluence. So you get a socio-economic result that leads to an increase in what we might call the middle classes. So broadly speaking, there are around 2 billion people who sit within what we might define as the middle class globally today. This is set to grow to around 5 billion people by 2030. And a large component of this new middle class will be from the developing economies of Asia. And of course, with this growing affluence comes changing demands from changing lifestyles, and this leads to an explosion in demand for building comfort, internal space comfort, and indeed for food products that are fresher and require a chilled supply chain. But of course, with urbanization, increased affluence, often comes a lifestyle that involves being in the home less and cooking less. So a demand for convenience food, often frozen, and a demand for increased health care, which comes back to the point around vaccines and medicine. And in fact, if you look at the typical purchasing pattern with increased affluence right across the developing economy, you'll see that the purchasing of cooling, either in refrigerated form or in human comfort form through fans or air conditioning units, fits within the first 3 purchases that a household makes once their level of affluence increases. So you'll see here a juggling of positions depending on which part of the world you're in, but basically it's a juggling between getting a television set, a refrigerator, or a fan. And so, it is without question that as areas of the world become more affluent and those areas of the world become warmer, we will see an explosion in the demand for cooling. So what might that look like? Well, Professor Peters and his team did undertake some work back in late 2018, early 2019, where for the very first time they tried to provide some projections of what cooling demand might look like into the future, based both on current trends and expected trends, and indeed on trends that might allow people to access cooling to the level that's required of the Sustainable Development Goals, in essentially cooling for all. So if we just take a base kind of view, which says, what if we went on with business as usual, allowing for increased demand as a result of increased affluence around the world, then we would see that by 2050, we would be looking at increasing the deployment of cooling equipment across the world. So this is both space. This is across all those applications of space cooling, refrigeration, and mobile cooling, from around 3.6 billion units in 2018 through to 9.5 billion units in 2050. And because of equipment replacement and redundancy and decommissioning and take up of new equipment, that would represent sales of around 19 billion units over that time frame. The energy implications of that and the CO2 equivalent emissions implications of that are quite staggering. So, as I mentioned earlier, we currently consume around 3,900 terawatt hours a year in meeting cooling provision. That would be projected to increase to around 9,500 terawatts a year by 2050, which, by the way, is well in excess of the International Energy Agency's allocation for cooling within a 2-degree scenario projection, which, in fact, it's about 50% over. And in terms of CO2e emissions, we would see an increase from around 4 gigatons today to around 9 gigatons by 2050. But as I said, Toby Peters and his team went on and they had a look at what the input pack would be if we looked at meeting cooling needs rather than economic driven cooling demand. They're quite significantly different. Whether somebody needs cooling is very different as to whether they have the economic power to be able to demand cooling. And if you take a look at those numbers, and I'm not going to talk them through now, but they are quite staggering. We would potentially see over the same time frame the energy consumption move to 19,600 terawatt hours a year by 2050, and the CO2 equivalent emissions hitting around 19 gigatons, which is easily half of current global emissions in total from all sectors. Okay, so clearly we're going to see substantial demand. Let's just drill down in a little bit more detail in that, and then consider what we might need to do about that as engineers working within climate change mitigation, adaptation, and indeed looking to develop a more sustainable world. So let's just take a quick look at global space cooling. I already mentioned the proliferation and ubiquitous uptake of these air conditioning units. So if we look globally, we expect to see an explosion in demand for global air conditioning. In fact, it's projected to grow around about 33 times this century. And if you look at the graph at the bottom to the right, you can see the plot of the expansion of air conditioning energy consumption compared with heating. So we see, as in the northern hemisphere, we get warmer winters. The demand for heating will level off and reduce. And indeed, here in the northern hemisphere, we will start to demand cooling, largely in the summer, when our summers are predicted to be hotter and significantly drier, with drought periods. Then we would see air conditioning balloon out as a result of that. But of course, enormous areas of the world that are currently developing economies will also be experiencing significant warming and demanding air conditioning and associated with their socio-economic development. And indeed, you see that at some point around about 2060, air conditioning demand outstrips heating demand. And indeed, if you just think about the EU in terms of which is obviously a northern hemisphere region, we're expecting EU-based population demand for cooling to result for space cooling to result in a 70% increase in space cooling demand by 2050. So something really needs to be done about this if we're going to have any chance of mitigating these impacts on climate change and moving towards a net zero economy, both here in the UK and elsewhere. I'm just going to give a couple of engineered examples of the sort of solutions we might think about at a kind of like individual solution level. So within the built environment, there's a really interesting technology that was developed in the United States by a company called IMechE. I give the website at the bottom there for you to take a look at. But this is a really interesting technology that was actually developed not specifically to meet this challenge of increased cooling and sustainability, but largely to shift electricity demand on utility power grids from periods of peak consumption to periods of low consumption to help to mitigate the impact of air conditioning on the energy system during the afternoon in hot southern states of the USA. So you'll see here that this is a hybrid where electricity in the nighttime period, when it's low priced and off peak, is used to freeze the liquid in that vat behind the air conditioning unit itself. And indeed, in the day, when the day starts, the air conditioner performs as normal using its vapor compression cycle. But then, when the energy consumption goes up and prices go up for electricity, it switches to using the cold store, the frozen cold store, as a means of providing the air conditioning, and it does so for up to maybe 6 hours of operation, by which time the peak has passed, electricity demand has dropped, and the equipment can revert back to using grid electric to drive the vapor compression cycle. So, a really good innovation that has potential to be used, particularly if it's used with renewable, low carbon energy sources for the charging phase, to help mitigate the impacts of cooling on the energy system. So if we have a look here at other options, I mean, typical options that we might think of reaching for could include district cooling, which of course is a variation on the well-familiar and well-trodden route of district heating. And in this case, we would use a centralized set of chillers, possibly associated with some natural cooling body, such as a body of water or underground aquifers, to enable us to cool an urban area of buildings through a district approach, rather than using those individual units. And of course, we could think around powering the chillers with renewable energy to increase the sustainability even further. So you can see a couple of ideas there. And if you think about the built environment, but more specifically around data centers, I've already mentioned the challenge there. There are 8 million data centers currently globally, and it's growing extremely rapidly. We need to think of approaches to data center cooling that don't simply rely on grid-connected chillers, which are typically used in the back of the building, in a plant room or at the back of the server space, to cool the system using typically air circulated cooling. So we might think about, for example, this novel approach being used in Sweden, which sort of talks to a couple of slides back in a way, in that it's using a heat network, a district heating system to distribute the heat that is produced, or if you like, is rejected by the data center as a result of the cooling process. And this can really have a significant, make a significant contribution to the heating, particularly in areas that have a cooler climate, even in the middle of summer. So, for example, this is an example from Stockholm. So, a lot of options, a lot of things for us as engineers to think about, a lot of innovation, a lot of novelty to be done in the build space. But of course, that also maps across into the food supply chain. And we've already touched on cold chains, both for food and vaccine. And indeed, cold chains rely on that transportation step to make them mobile. Without that, you don't have a cold chain. And the current solutions for transport refrigeration use technologies that are problematic both in terms of their greenhouse gas emissions, but also in terms of other pollutants that have air quality degradation impacts in urban environments, such as NOx and particle matter. This is an area that is ripe for solutions that provide a multiple range of benefits. In fact, you may have heard one potential solution covered a couple of weeks ago on the latest BBC Radio 4 program, 39 Ways to Save the Planet, where they dedicated an episode to looking at technology driven by the Dearman engine, which aims to use liquid nitrogen or liquid air to help meet future demand for transport refrigeration units in a more sustainable way. And this slide illustrates the sort of demand that we might see in the next 5 years for increase in transport refrigeration units as a result of developing economies looking to reduce their loss of perishable product and the spoilage of perishable product as a result of a lack of that transport link within the food supply chain from field or fish landing to fork. So many areas being explored technically for solutions, as well as the Dearman engine. And there are a number of them that I list on this slide with the various benefits and challenges associated with those. I won't go through those now, but that will be there for you to have a look at later if you so wish. So my key point really is that we need a new approach to cooling. That is an approach that is far more sustainable and enables us to meet these socioeconomic demands from growing affluence in developing economies, and also that overarching challenge of adapting to climate change while simultaneously mitigating future impact on climate change and by reducing our emissions and working towards a net zero system. So we started thinking about this at the IMechE probably around 5 years ago, when I led a project which looked at the food system element of this and how we might develop a more sustainable food supply cold chain. And in fact, you see the report there that we produced a tank of coal, clean tech leapfrog to a more food secure world. And in this, we explored a whole range of options for improving the sustainability of the food supply chain, which of course have implications also for the vaccine supply chains, particularly with a particular focus on the developing economies. And in that, we postulated in collaboration with Professor Toby Peters the concept of the cold economy. In fact, Toby was a major or I should say the lead thinker of that within our discussions around this within the project. And indeed, Birmingham took this work forward. You can see a report they produced fairly soon after the IMechE report there, where they looked at the whole area of doing cold smarter. And here, this is really about needing to reshape the way we address cooling needs, to think about cooling energy demand as individual elements of the demand, not as part of embedded in overall energy demand. So what I mean there is thinking about cooling demand per se, rather than it simply being about electricity provision and electricity demand. And we need to think about using other sources of cooling that are readily available to us, like waste cold, in the same way as we have for the last couple of decades been searching to use waste heat. In heat recovery, we need to do cold recovery, and we need to pay more attention to natural sources of heating that are available around us. And in fact, a huge amount of work has been done on this now in the intervening years, where we've been looking at cooling provision within the through the lens of the energy hierarchy, which of course is something that the IMechE developed about a decade ago, around about 2010. Has been a very successful lens for looking at how we approach energy system problems, and starting with energy conservation and moving to energy efficiency, use of renewables, other low emissions technologies, and then if we have absolutely no other way forward, using conventional fossil fuel-based technology, but with mitigation adaptations such as carbon capture and storage. So, there's a whole area around how we use cold, how we make cold, how we move it around through energy vectors, and how we manage cold intelligently using state-of-the-art IT infrastructure, Internet of Things, these sort of approaches, control systems and systems level management that requires to be addressed as engineers to move this whole cooling system towards a more sustainable space. So, as well as sort of engineering and the technical aspects that many of you listening will be most interested in, because there's a need to develop new business models and new policy approaches to enable us to implement these technologies. And new areas that we might think about are the provision of cooling as a service in developing economies, as an alternative to the more traditional model of equipment purchase and ownership. So this is effectively a servitization of cooling provision. And the reason this is becoming very popular in developing economies is, of course, because of the affordability of the cooling technology. So rather than individual farmers or fishermen looking to gain their own cold store, and indeed coal vehicle technology that has cooling on board for payload, which is relatively expensive in developing economies, this enables a service provider, a local entrepreneur, or a local farmer cooperative, or an aggregated group of farmers to offer cooling as a service on a per pallet or per ton basis. And what we find is that within the developing economies of the world, the synergy between this and the need to find off-grid solutions as a result of lack of good grid connectivity leads to the uptake of renewable solutions like the one shown in the photograph, where we have solar panels powering a small cold store that services a large number of smallholder farmers. Of course, we must remember that about 80% of the farmers in the world are smallholders working around a hectare of land, 1 or 2 acres of land in their holding. And so aggregation and service provision of cooling is a major step forward for them in terms of getting their food to market in a more robust and higher quality state, which of course affects the price. So I just want to finish with just saying a few words about the fact that we need to take a systems approach to cooling. It's not just about those individual point solutions that I've been talking about this morning. We need to look at this as engineers as we do in many other areas, through a systems lens. And that system doesn't just mean the technology elements of the system. It means we have to understand the policy element of the system, the commercial element of the system, the financing end of the element of the system, and how all of this comes together to produce a technical, socio-economic, and politically acceptable solution that is within a big picture and composed of many systems of systems. So there's much more work to be done on that. But again, the team at Birmingham, particularly the Sustainable Cooling Centre, which is led by Toby, are doing extremely good work in this area. We ourselves at the institution, in that report that I showed earlier, began exploring something that has become known as the Community Cooling Hub, in which that servitization model of cooling provision is used to provide cooling to a number of users within a developing economy rural setting, for pre-cooling of food produce, vaccine and medicine storage, and space cooling, not only for work but education and leisure, and indeed enables those rural economies to transition into higher value food processing. And of course, you can imagine a model here which might have two ways of being achieved: one through co-location of sources of demand with a hub supply point. So that's kind of like an industrial estate model that we would recognise here in the UK, or indeed the introduction of a whole new energy vector for distribution around a cooling hub supply point, which might actually be the end point of a cold chain. So more of that within that report, and I extended this in a paper that I wrote a few years for Tropical Agriculture Journal. And indeed, Toby and the team at Birmingham have taken this forward in an on-the-ground project in India in recent years, exploring how to actually do this in an Indian rural setting. So just finishing, there's a huge range of cooling technologies that you as an engineer, particularly if you're a young engineer, fresh into the profession, might think about tackling, and you might want to have a look at this slide and consider how you might fit into this exciting area that really would add value to mitigating climate change and moving us towards net zero. And of course, much of this existing technology is based on vapor compression cycles and needs to be replaced with technology, innovative, novel technology. But of course, that technology has to be affordable, safe, easy to use, and easy to maintain. And of course, we have to be cognizant of the need to train and develop skills for people to deploy and use that technology, and of course decommission it. Lots of work going on. I won't say too much about that, but if you're interested, there's a slide there that shows a range of innovation going on around the world in the cooling area, and it's an expanding area of work. A lot of work going on. These are just a few reports from a couple of years ago. There's been an explosion in reports coming out on cooling recently as a result of the early catalytic work that Toby and myself did back in the 2014, 15 time frame. And you'll see here the work that some of the numbers that have been provided in this talk have come from. A call board defining the energy conundrum of cooling for all. It's where we explored the use of cooling to meet cooling provision need, or the use of sustainable cooling, or the need for the use of sustainable cooling to meet the SDGs. And of course, most recently, we're all familiar now with the importance of the cold chain and its central importance to the COVID-19 vaccine distribution challenge. And in fact, again, Toby Peters and the team at the Centre for Sustainable Cooling in Birmingham led a piece of work that I was involved in reviewing and editing to produce this report that looked at the challenge of delivering those vaccines in the developing economy and developing economies and least developed economies of the world. And I encourage you to have a look at this. It's about filling the gap, doing something about the deficit of cold chain that already exists in these economies, but ramping up that capacity to meet the demand of COVID-19 vaccine distribution, and of course doing it sustainably with a view to meeting the Paris Agreement and the SDGs, and not simply business as usual with deploying current technology. So I'd like to thank you for your attention. Just to sort of wrap up, coal is ubiquitous. It's a fundamental part of the modern energy system, but it's not recognized. Cooling demand is set to increase dramatically as we move forward in a warmer world, and with increased socio-economic power in developing economies. And we clearly need to do something very different about its provision. Thank you very much. I'm going to hand back to Jack now, who will chair a question session. Jack.
Thanks a lot for that, Tim. Right, so we've got a question here. The question is, as stated, cooling is a significant energy cost for supermarkets and therefore a significant cause of CO2 emissions. This cooling demand could be massively reduced if all the display cabinets were fitted with doors. What is stopping them from doing this, in your opinion?
Yeah, so thank you very much for that. Yeah, I mean, this has been a problem that again was identified in that report that we produced a few years ago, and indeed a number of organisations have taken up that demand. And the basic reason for not having the doors on the chiller is, of course, consumer convenience, in enabling them to access the product on the shelf as quickly, easily, and uninhibited with no barriers as possible to encourage purchasing. But of course, from a sustainability point of view, it doesn't really make much sense. So there has been a lot of work that's gone on, around ways in which you can have the produce on the shelves can be protected through directional cooling. So effectively aerodynamics, so that as much of the cooling as possible is kept within the display area. That's one approach, because you'll have noticed, many shops have implemented sort of like plastic streamers, blind, effectively like the blinds you have in a room that enable you to still see produce and reach inside and get it, but still don't have the barrier of opening a door. Those kind of approaches. But yes, agreed. I mean, one of the things you'll notice if you go to a supermarket, you'll notice immediately on a hot summer's day that you suddenly become very cold because the cooling of all the product chillers has been turned up, and the whole store is quite chilly. And then sometimes you have the ridiculous situation of having to reach for a pullover when you enter a supermarket on a hot summer's day because it's too cold inside. So yeah, it does need attention. Thank you.
Right, thanks for that answer. Right, another question is regarding the loss of productivity due to the lack of cooling. Do you think this has got worse in the pandemic due to working from home? For example, like a lack of cooling that's present at home.
Yeah, that's a really interesting question. That's a whole area of work that needs to be explored, and indeed a number of people are beginning to think about that, because clearly, if we are going to see a shift towards working from home as a permanent feature post-pandemic, which, because we are expecting to some degree that much of the workforce will not return to the office ever, because of the benefits of working from home, both to the commercial organisation in many cases and the individual. There's potentially some real challenges there around future hotter, drier summers, leading to heat stress in homes that are not designed to cope with those climatic conditions. So a huge amount of our housing stock here in the UK, for example, is not designed to be resilient to future temperatures in a 3 or 4 degree warming scenario, which translates into significant temperature rises in a place like the UK. We may see 10 degrees higher temperatures in summer, for example. So there's obviously health implications for that, and there's obviously productivity implications for that. So it is an area that is beginning to be explored, and is part of a broader consideration of how we adapt our housing stock to meet cooling demand, because what we don't want to do is pop down to our nearest hardware provider, not mentioning any names, pop into that store and buy a air conditioning unit on a hot day when we've just about had enough, take it home and plug it in, and contribute to climate change. Which here in the UK, we're fortunate enough that we have a energy system that is decarbonising, so less of an issue than in other parts of the world where, of course, you've still got fossil-based fuel for electricity production. But yeah, needs careful analysis and assessment and a strategy for dealing with that.
Thank you. And another question is, what role can passive cooling solutions such as insulation or redesign of cities to counteract urban heat islands effects play? And what appetite is there for implementing passive cooling solutions?
Yeah, so this is really important area. So I just want to touch for 2 seconds on urban heat island effect for those that are not familiar with it. So this is about how city centres of urban conglomerations are often significantly hotter than the surrounding rural landscape. So it could be up to 5 or 6 degrees hotter. And of course, if you implement air conditioning and fill the city up with individual air conditioning units strapped to the outside of buildings or chillers, you're exhausting all that excess heat from the chillers and the air conditioning units into the local environment and exacerbating the heat island effect. So it's absolutely critical that we find ways to reduce demand for cooling in urban environments, as well as transition approaches to cooling in urban environments to be less energy consumptive. And a part of that, of course, is to go for non-mechanical approaches to cooling, such as the use of shade, the use of natural ventilation, and the use of different types of glass that have a internal cooling effect. There's a lot of work going on around that, but of course we always come back to this issue that we as energy system people come across that a huge amount of the challenges around existing building stock and how we retrofit that. So new builds with passive design, integrating those kind of features is one thing, and should really be the norm. But retrofitting is extremely challenging, and there's a lot of room for and a lot of scope for that. The situation with insulation is interesting. I have done a bit of work looking at this, and clearly insulation potentially has an effect of trapping heat inside buildings if other elements of passive design are not integrated at the same time. So we do have to be careful with that. And that is part of the sort of climate change risk assessment analysis. Thank you for that. It's a good question.
And another interesting question here is, what would be the best technologies to recycle waste heat to generate cold? I suppose we've seen an increase in the number of sort of heat pumps being implemented around homes instead of traditional central heating systems. Is there any way that maybe that can also be used to generate cold as well?
Yeah, so sort of the standard sort of technical engineering process is absorption technology. So this is a well-trodden route in terms of taking heat and turning it into cold. And there's a lot of research and development existing technology around that. That's the sort of standard route to that. Adoption is really around needing to ensure that the equipment that is produced is, as I mentioned towards the end of the talk, is affordable and is easy to install, maintain, and decommission. That's the absolute key to anything we want to make available globally. So there are many areas of the world that don't have the same, or are not fortunate enough to have the same range of skills and depth of technical expertise that we're fortunate enough to have here in the UK. So there is, yes, that's the sort of standard route.
And I think we've probably got time for one or two more questions. So one question is, which is quite interesting, is who will drive the implementation of efficient cooling units, and how do you think we can sort of help developing economies and developing countries do this as well?
Sorry, Jack, could you just repeat the first part of that?
Yeah, of course. It's who will drive the implementation of efficient cooling units and systems, especially in developing countries where obviously the finances aren't as available.
Yeah, so there's lots of strands potentially to that. Like all these things, there's not one silver bullet. So often we look for a silver bullet technology. There's not a silver bullet policy solution either, or a silver bullet commercial solution. It's a range of potential drivers and solutions that are really from a smorgasbord of drivers that you find all over the world. But once you get into a particular country or a particular jurisdiction, that a particular set apply, and it's a question of finding those by understanding the socio-economic, political landscape of the particular nation or block of nations that you that work with. But there, at a kind of more generic level, at a global level, there is a strong push to encourage countries to develop national cooling plans. And indeed, India is a good example of a nation that developed a national cooling plan very early on. They're one of the first nations to do so as the UN call for such came out. And these national cooling plans, should really be part of the Paris Agreement, maybe future net zero strategy for moving towards a net zero outcome. And if I can just go back to India, I mean, in many cases, these plans can align with local ambitions. When I say local, I mean nationally, in terms of uptake of clean energy more broadly, so renewable energy systems, and indeed with sort of socio-economic development and industrial development. So it's really a question of looking at an individual country through its particular context lens and finding the appropriate policy and commercial drivers for those countries. So I'm sorry not to be able to give a silver bullet answer to that.
I think on that note, due to the time constraints, we're going to probably have to round that off as our last question, if that's okay with you, Tim.
Absolutely, yeah. I know we're scheduled to finish at 12 and we're getting close to that, so thank you.
I just wanted to thank you all for coming today and thank you all for attending. You should be emailed a digital copy of this presentation in a few working days to come. And yeah, that concludes the end of the presentation. Thank you very much for joining.
Thank you.